area with respect to that function. But at its core, this notation is telling me that if I had some function that was equal to, well, okay. If I had some function, its derivative is equal to 1 over 2x plus 3. And it happens that that function is 1/2 the natural log of 2x plus 3. So when we're asked to find an indefinite integral, meaning we don't have limits of integration, it's saying there's some function out there whose derivative is 1 over 2x plus 3. What is that function? I don't want to move forward with partial fractions until this feels easy. Because the entire reason to do partial fractions is to break it down into a bunch of things that look like this so that we don't have to work hard to integrate them. If I just had 1 over x plus 3 dx, I think here most people are going to say pretty quickly, oh, that's natural log, because this is the derivative of natural log of x plus 3 plus a constant. But what I want to emphasize is even if I throw some additional numbers in here, like 3x minus 4, we can still pretty quickly get to an answer over here. If for you writing out the u substitution makes that feel more comfortable, it's totally fine to write out that u substitution. Just be thinking about working towards maybe not needing to write that. Here I have a number and a linear term in the denominator. So that number 5, I can always choose to put out in front of the integral. And this part here, if I were going to write out the u substitution, I would end up with u is equal to 3x minus 4. So the derivative would be 3 dx. And to get that dx by itself, I would need this to look like 1/3 du is equal to dx. Every time that we have this situation where I've got 1 divided by a linear term, something that looks like a line, this same thing is going to happen in that u substitution. And whatever the coefficient in front of x is going to end up as a 1 over that coefficient when you make the u substitution. So rather than actually doing the u substitution, I'm going to jump to the thrilling conclusion here that I'm going to end up with 5 over 3 natural log absolute value of 3x minus 4. Does anyone want one more example like this, or can we move on? Thank you. Plus C. Yes, let's get all of our points. Well, if I wanted to add these, I would need to get a common denominator. So I'd multiply this guy by 5 over 5. I'd multiply this guy by 7 over 7, 5 over 5. That is really doesn't even look like a 5. Still doesn't look like a set of 5. It's okay. 5 times 3, I'd have 15 over 35 plus 14 over 35. And the whole reason that we're doing that is so we can combine the numerators, and I'd have 29 over 35. I am not asking you to do anything with numbers and fractions, but suppose that I told you that we got down to a final answer of, I don't know, 5 over 12. What were some possible denominators that we started with? You can type numbers in the chat. So we worked on some fractions, we were adding or we were adding some fractions, we needed a common denominator. We worked it out, we got 5/12. Now I want to think backwards. What were those possible denominators? I got a 3 as a possible denominator, a 4, I got a 6, I got a 2. Yes, technically we could have a 1 as a denominator, and I suppose we also could have had that 12 as a denominator. Well, the whole idea with partial fractions, with rational functions, is we're starting from this end result and basically trying to guess what were the fractions that we started with that combined together to give us that other thing. So now for the real example. None of that needed to be in your notes. This next part should. Suppose I've got an integral, and let's do x squared minus x minus 6 and 2x plus 5 in my numerator. So I'm going to walk up to this integral and I'm going to say, hey, it's just algebra. I've got x's raised to powers. Sure would be cool if there was a u sub to do. But if I look at the denominator and take the derivative of that, I'd have 2x minus 1, which is not what I have in the numerator. So now I'm thinking, well, it wasn't a u substitution. There must be some kind of algebra to do. Hey, does the denominator factor? Why, yes, it does. That denominator factors as x minus 3 times x plus 2. Well, the reason that that's important is now I know that if this thing came from some sort of fraction where the common denominator was x minus 3 times x plus 2, then the possible fractions it came from had denominators of x minus 3 or x plus 2. We're going to use that to simplify the integral. So because I know that I'm a little short on board space, I'm going to get rid of my integration symbol and just concentrate on thinking about how to rewrite this. So I'm going to say that this came from getting a common denominator for a fraction that had a denominator of x minus 3 and another fraction that had a denominator of x plus 2. Well, I don't know what either of those fractions were, so I'm going to put placeholders in here. I'm just going to call this A, and I'm just going to call this B. There are at least 2 choices for how to work through this problem, but our intent is to solve for the values of A and B. Both options work 100% of the time, but usually for a given circumstance, one option is a little bit faster or easier on the algebra than the other. So I'm going to show you my favorite version, and if y'all hate it, we'll do the other way. Oh, so sorry. Thought my phone was on silent. Now I can't seem to put it on silent. Okay. So my favorite version is to look at this and to get rid of all the fractions by multiplying both sides by the common denominator. So I'm going to multiply by x minus 3 times x plus 2. And over here, I'm going to multiply by x minus 3 times x plus 2. So on the left-hand side, all of my factors cancel out, and I'm left with 2x plus 5. On the right-hand side, when I distribute this in, when I distribute into the first piece, the x minus 3's will cancel, but I'll still have the x plus 2. And when I distribute into the second piece, the x plus 2's cancel, but I still have the x minus 3. So this is where the 2 different versions of finishing this off come from. Personally, I just plug numbers in. An alternate method is to multiply everything out over here and end up with a system of equations. I'm going to plug in, and like I said, if you hate it, I'll do it the other way. Here's what I mean by plug some numbers in. If we're really going to find an A and B here, it has to work for every value of X. Otherwise, these two things are not always equal. Well, if it works for every value of X, let's choose the lazy values, meaning the value of X that would make this 0 and the value of X that would make this 0. So if I choose to let X be equal to -2, then on my left-hand side, I've got 2 times -2, -4, plus 5, so I'm at 1. But when we plug in -2 here, that whole thing is going to 0. And when I plug in -2 over here, -2 minus 3, so that's -5. And I already know what the value of B is. B is going to be -1/5. My other nice number to plug in would be 3. So if I plug in X equals 3, now I've got 2 times 3, so that's 6, plus 5, makes that 11. And when I plug in 3 here, 3 plus 2, I'm going to get 5. When I plug in 3 over here, 3 minus 3, this whole thing is going to 0. And now I've got a value for A. Once we know our values for A and B, then we can come back and finish off this integral. Okay, there's a question in the chat, so I don't want to ignore it. Got it. Okay. So the question in the chat is because I talked through a step and I didn't actually write it out. So let me talk through it again, or maybe try to write it out. When I multiply both sides by that common denominator to eliminate the fractions, well, over here, the entire denominator cancels out. Here, if I think about taking the x minus 3 times x plus 2 and distributing that into the first piece, then if I was writing out that entire first piece, I would have a divided by x minus 3, but then these two are both getting multiplied in the numerator because that's where we multiplied them on this side. So if I keep going on this numerator, I'd have x minus 3 times x plus 2. So those x minus 3s would cancel out, and I would just be left with the a times x plus 2. So that's the only part that I wrote here, was the a times x plus 2, because the x minus 3s cancel. Similarly, when I take this and distribute it to the second piece, I could write this whole thing out, but this time the pieces that would cancel are my x plus 2s, and I'd be left with b times x minus 3 in the numerator. So the whole reason I'm doing it is so that I don't have denominators at all anymore, so that it's going to cancel out with one of the things that I'm multiplying by. So we did all this work, we did all that algebra, so that we can say that integral right there is equivalent to finding an answer for this integral right here, which we can break apart into two pieces, and I can take that 11/5 and pull it out in front of an integral, and then I can take that -1/5 and pull that out in front of my other integral. And this is the part where, if we're good at that kind of basic set of antiderivatives, then when we get to this point, we just write the answer. We say that's 11/5 natural log x minus 3 minus 1/5 natural log of x plus 2 plus a constant. So I'm going to walk over to the integral, and I'm going to say, hey, it's just algebra. But I sure hope the derivative of one part equals the other part so I can do a u substitution. Well, let's see. If I were to take the derivative of the bottom, I'd get 4x plus 1, which is not what I have on top. So I'm not looking at a u substitution. So the next thing I'm going to ask myself, if it's just algebra and we have a fraction, is I'm thinking, hey, does the bottom factor? Does anyone see how the bottom factors? You could type it in the chat if you see the factors. Great, I see how it factors because I wrote the problem. By the way, I cheated when I wrote the problem, and that's how I know that it factors. When I'm writing the problem, I just think about what would I have to plug in for x to make it equal to 0. So I can start with anything I want, pick a value for x, and that tells me what to make the last part equal to. So I got here, and I said, well, if x was equal to 1, then subtracting 3 would make the whole thing 0. So that's how I know that one of my factors is x minus 1. So I'm going to get 2x plus 3. Now that we're here, I'm going to say this came from combining two fractions and getting a common denominator. So one of those denominators is x minus 1, and that other denominator was 2x plus 3. I don't know what the numerators were, so I'm going to put placeholders in of a and b. Next, I can take the entire thing and multiply by that common denominator to eliminate all the fractions. Oops, 2x plus 3. And over here, I have x minus 1 times 2x plus 3. Well, when I distribute all that out, on the left-hand side, we're just left with 4 plus x. And on the right-hand side, when we distribute out, when I multiply into the first piece, the x minus 1s will cancel, and I'll be left with a times 2x plus 3. And when I distribute into the second piece, I am left with b times x minus 1. Rolling from here, we have two methods for solving these. Would anyone like to see the other method, or should I stick with plugging numbers in? You can put it in the chat if you want to see the other method. Great, let's see the other method. By the way, they both work every time. Don't let anyone tell you otherwise. It's just that sometimes one is less work than the other. So here's the other method. I have to multiply all of that out. So on the left-hand side, I've still got that 4 plus x. And over here, I'm going to distribute the a in, so I'll have 2ax plus 3a, and then plus bx minus b. Now I compare the two sides, and I group the things that go together. So what I mean by that is over here, I have a 4 that does not have an x attached to it. So I want to match that 4 up with the pieces on this side that don't have x's. Because if these two things are going to be equal, then the part that are numbers over there has to be equal to the part that's numbers over here. So I'd end up with an equation that says 4 is equal to 3a minus b. Then I'm going to take the parts over there that have x's, and secretly there's an invisible 1 in front of that x. And I need that to match up with the parts over here that have x's. So I would have an equation that looked like x is equal to 2ax plus bx. Or if we factor the x's out on both sides, I'd have 1 times x is equal to x times 2a plus b. And since I've got an x on both sides, I can actually say 1 is equal to 2a plus b. And then solve this system of 2 equations and 2 unknowns. Any way you want to solve for the 2 equations and 2 unknowns. For me, I'm looking at that and thinking, well, gosh, if I just add both of those equations together, the b's will cancel out, and I would have 5 is equal to 5a. So a would have to be 1. And if we already know what a is, then we can take either of the equations, plug a in to come up with a value of b. So if I look at that bottom equation, that 1 is equal to 2 times a, but now we know that a is equal to 1 plus b. Subtracting that over, looks like I've got -1 is equal to b. I'm not ignoring the question in the chat. I'm going to bring it back around right now. So the question was about, does it matter which one the a and the b goes with? Absolutely not. We just want to be consistent throughout the problem. So here, now that we're done, what is important is that I wrote my a on top of the x minus 1 term, which means that when we're writing this integral and swapping it out, I just need to make sure that my 1 goes with wherever I put the a in my equation. So if you had factored this as 2x plus 3 times x minus 1, it would just mean that your a and b were swapped. You should get the same numerical values for the 2 numbers. You just have to be careful to make sure they end up on top of the right part for your version of the factoring. So my a was 1, so I'll have 1 over x minus 1 plus, and now b was -1, so -1 over 2x plus 3. And I think I can squeeze this in. I'm looking at the natural log of x minus 1. And if we haven't talked about this before, those absolute values, don't get too frustrated in WebAssign. If it's telling you your problem's wrong, check for that plus c, but also if you've got a bunch of natural logs, check for absolute value. So I've got ln absolute value of x minus 1, and here, that's that thing where I've got a number in front of the x. So I know that when I take that antiderivative, I'm actually going to end up with -1/2 ln 2x plus 3, and then whole thing plus c. You could check for a u substitution. It's not a u substitution. The bottom's already factored for us. Let's just assume we're on a partial fractions kind of roll. Well, when I look at this, I can see 2 denominators, right? I can see that I'm going to have an x squared and an x minus 3. But it's that x squared that I want to talk about for a second. Here's my short version, and it's basically the version that the textbook gives. If you have a quadratic term in the denominator, then you need a linear term in the numerator. The more generic thing would be to say, whatever the power is of x on the bottom, we need the power on the top to be 1 less than that. So if I have an x squared in my denominator as one of those factors, then my numerator would actually look like ax plus b, to put a linear term on the top. And then that would mean that I need a third variable over here, c. I don't actually solve this problem like this, though, because this I can simplify. And I can think about that as saying ax over x squared plus b over x squared plus c over x minus 3. And the convenient thing about that first one is that one of the x's cancels out. So I really have a over x plus b over x squared plus c over x minus 3. I'm going to do the same thing that we did on the other problems, which is I'm going to multiply by the common denominator to eliminate all of the fractions. And I want to be careful when I do this. So the common denominator is x squared times x minus 3. And when we multiply by that x squared times x minus 3 and distribute it out, we just want to be careful on the right-hand side. So over here, all of our denominators are going to go away, and I get 2x plus 1. And over here, when I distribute that into the first piece, one of the two x's will cancel, and I'll be left with a, x, and x minus 3. When I distribute this into the second piece, both of the x's will cancel, so my x squareds will go away, and I'm going to have b times x minus 3. And then for the last piece, when I distribute it in, the x minus 3's will cancel, and I'll end up with c times x squared. If we were going for the method of plug nice numbers in, I only have two nice numbers to plug in, 0 and 3. But I have 3 variables to solve for. I've got an a, b, and a c. So if we go the route of plugging the numbers in, we're still going to end up with some kind of additional work that we have to do. So this is usually the case where people will think, oh, it's easier to just multiply it out and solve a system of equations. I don't usually want to solve a system of equations of 3 unknowns. So I'm going to go ahead and plug numbers in, even when I run out of nice numbers. So if I start by plugging in 0 for x, then on the left-hand side, 2 times 0 plus 1, I've got a 1. When I plug in 0 here, that's going away. My next piece, when I plug in 0, I'll have b times negative 3. And my last piece, when I plug in 0, that's also 0. So here at least I got b. B is going to be that negative 1/3. My other nice number to plug in is 3. And if I do that and plug in x equals 3, on the left-hand side, I've got 3 times 2, so 6 plus 1, I get 7. When I plug in 3 here, I get 0. When I plug in 3 here, I get 0. And when I plug in 3 here, 3 squared is 9, so I've got 9c. So now at least I know what c is. C is going to be 7/9. I'm out of nice numbers, but back to something I said before, if this equation is going to be true and usable for all values of x, then I can plug in any value of x. It doesn't matter. So I'm just going to pick something easy to compute, like 1. And if I plug in x equals 1, then on the left-hand side, 2 times 1 plus 1, I've got 3. On the right-hand side, I'd have a times 1. I'll just write it out. A times 1, and then 1 minus 3, so it's negative 2. We already know that b is negative 1/3, so I can go ahead and plug that in at this point. So I'd have negative 1/3. And then when I plug in the 1, 1 minus 3, I'd get negative 2. And I already know what c is. C is 7/9. And x was 1, so times 1. It might not be pretty, but given time, energy, sufficient monetary motivation, and maybe a calculator, for sure we could solve for a. I picked these numbers at random, so it got a little messy. Should we finish it off? Should we figure out what a equals? Yeah, why not? Let's do it. Okay, I just didn't leave myself a ton of space. So I'm going to erase the B and the C. I'm going to plug them in up here because we already know what they are. So B was negative 1/3. And C was 7/9. So I'll get that up here. And then I'll figure out what the heck A is. Well, if I look at that equation, left-hand side, there's not really anything I can do to that. Here, I'm going to rewrite that as negative 2A. Negative 2 times negative 1/3 is a positive 2/3. And plus 7/9. I hate fractions, or rather, I'm more likely to make a mistake with fractions. So I'm going to multiply the whole dang thing by 9. 9 times 3, 27. 9 times negative 2A, negative 18A. 9 times 2/3, the 9 and the 3. Those are going to reduce to leave me with a 3 on top. Times that 2, I'm looking at a 6. And 7/9 times 9 is going to be 7. 7 and 6 is 13. And if I subtract that from both sides, I'll be down to 14 is equal to negative 18A. And we've almost got it. I'm looking at negative 14 over 18 is equal to A. Or if we wanted, both of those are divisible by 2. And that's a negative 7/9. So now I know what A is. Negative 7/9. And we are ready to integrate this. I'm erasing my algebra. So this all started as the integral of that dx. We have now turned that into the integral of this dx. The hope is that we can just write the answer without thinking too hard. Well, this first piece, I have a linear term in the denominator. That's going to give me a natural log. And here I just have an x, so that's going to be negative 7/9 ln absolute value of x. Now this next one, when you've been doing a bunch of these, it's really tempting to go, oh, that's ln of x squared. But actually, I've got that negative 1/3. And 1 over x squared, that's not the derivative of natural log. I have the integral of 1 over x squared. Thinking about our antiderivative skills, that's the same as x to the negative 2. So I'm going to add 1 to the exponent to get x to the negative 1, and then divide by the new exponent. So this is going to be negative x to the negative 1. So I've got negative 1/3 times negative x to the negative 1. Here, I do have a linear term in the denominator, so I'm looking at 7/9 natural log absolute value. Oh, x minus 3, not x plus 3. X minus 3 plus a constant. Whole heck of a lot of work.